Welcome everybody to the Risk Management of Your HV Cable Network webinar. Myself is Brad Monaghan from Head of Services. We're in Brisbane, Australia, and this is Thomas White, Senior Engineer. Let's go to the next slide, Tomo. Cool. So this is the second part of a two-part series. Part one was your guide to HV cable testing. We ran that a couple of months ago, 20th of June. It covered offline and online cable testing, what can be done, the physical things that can happen in the field to get the answers that you need when you're doing those types of tests. It's available on our EA Technology Australia YouTube site, which you can see a screenshot of there. And now this is the second part. Okay, so what we're going to talk about today is a little bit about ourselves. Why do we test cables? Case studies. We're going to talk about a case study here today, and then we're going to expand on the thought process and the risk management part of the case study. Introduction to asset management methodologies, CBRM process, that stands for condition-based risk management, network analytics, health indexes, the condition monitoring tests, asset health forecasting, network risk analysis, interventions, and further modelling options. So I'll speak a bit at the start, then a bit of Tomo, then a bit of me, and then a bit of mostly Tomo. So that's the running sheet. So next one. So who is EA Technology? So back in the 60s, there's 6 power companies in the UK, and they all used to have their own section of research and development teams. In the 60s, they got all those people, put them in the one building, and they became the research council for the whole of the UK. That was all funded by the power companies, which is ultimately the government. In the 90s, they became privatised and took everything worldwide. In the 1994, they became EA Technology. So we have offices all around the world. We've got England, America, China, Singapore, and Australia is where our offices are at the moment. And we work closely with all electrical companies, high voltage, low voltage, and we have a lot of different services. Okay, so why do we test HV cables? So HV cables usually get tested, or always get tested, as part of the commissioning process. So you'll test their insulation. Are they safe to turn on? You'll stress their insulation if you want to run a VLF test on that. And then there's further tests that you can do, which are condition monitoring tests, namely partial discharge, tan delta. And there's a whole different range of tests that you can run. That was all covered in the previous webinar if you want to go back and run that. If a cable blows up, you will retest it again, and you can actively turn your cables off to condition monitor them as well. That's going to improve your asset performance, increase reliability and safety, running costs, smarter investment decisions overall. So when we look at some HV cable fault statistics, so this is a study that was done by Higginbotham and Higginbotham in America in 2018. They took a cross-section of cables that had failed and looked at the root cause of the failure. Workmanship was 57% of the cable failures. Aging was 11%, and all the other types of causes you can see there on the right-hand side there. Many studies have been done on many different cross-sections of cables. Workmanship is usually the cause. Usually cables blow up in their cable joints and in their terminations. That's just a pretty general, common piece of information that comes across there. Okay, so let's talk about our case study. So this is a large industrial site in Australia, established in 1981. Not much data on their HV cables other than what was recorded when they first built them. They have an aging network. Most of their cables on site are in cable trays. That means that we can visually look at the cables. They're like literally right next to your head as you are walking along. There's a mixture of XLPE and paper lead cables. If any of these cables fail, they generally have a high production loss on their output of their facility. So keeping these cables in service is critical financially and reputation-wise and all those types of things. They rely on contractors to conduct their cable works, the physical works to the cables, the building of them, the maintenance on them, and if any failures happen, fixing them as well. So the engineers are focused on long-term planning. How long have we got before we start to replace our cables? How long have we got before things are reaching their end of life? How long have we got before, what are some things we can do right now to increase their reliability. Okay, next slide. And that one's clicked out. We're back.
So,
oh, that's it. That's all right. So this project was initiated back in 2016, and we've since done 4 condition testing stages. So we've gone back every couple of years and tested a whole bunch of cables to get all that condition data to put into the CBRM process, put it through the CBRM process. Initiated as some HV cables were reaching the end of their manufacturer's recommended life, so their book life. Engineers are looking at establishing a baseline of the condition data, and then so we worked with them to come up with a suite of tests that were able to be done to get the best condition data to put into the CBRM process. They're focused on long-term planning. They want to forecast the health of their assets, and they want to figure out how much life's left in the end of their HV network.
So the bit of difference about today's webinar is we're not focusing as much on the condition data, but rather what we did with it, what the asset engineers took the data, what they used it for, and how we used it to forecast the asset health, determine the asset health where it is now, where it is in 10 years, and what the effects of different maintenance regimes will do on the network. So to do this, we used what we call the CBRM model, which is condition-based risk management. And it's a large overarching asset model where it combines effectively everything you have, every bit of information on your cables. This is our model that's based on the CNAIM methodology, which is basically, it was developed alongside EA Technology over in the UK with all of their energy companies. And it was put in by the regulator as a way of standardizing how we assessed our different assets. When people ask me to describe what these models do, I always tell them in reality, it is what asset engineers are doing in their head. If Brad or me come to site and we run a suite of tests on your cables and we tell you you've got a problem on a specific one, the first thing you do is you start to think to yourself, oh, well, that cable is a bit old. We have seen bad tests on it before. We have seen a fault. We've got a number of joints. And you start to piece together all of the information and you build a picture in your head of what you think the condition of that cable is. And then you start to think about what that cable means to you and your network. You go, oh, well, it feeds a quite critical bit of plant. We haven't got any redundancy on that. So we probably need to work on that quite urgently. And that is what the CBRM models and the CNAIM methodology is all about. It's about standardizing that thought process and giving you justification and an easily repeatable thing. Because it's all well and good when you're looking at one cable, but you have a lot more than just one cable and one asset to worry about. Energy companies will have thousands. Industrial sites may have hundreds, but it's not possible for an engineer to sit there and quantify all of that and give an easily a good representation of the health of every asset on your network. So that's what we did for this client. CBRM is very much a worldwide product, and it's very much a standard when you start with energy companies. This is something that nearly every energy company uses some sort of asset management methodology, and most of them, their roots are traced back to the CNAIM methodology. Today, we're talking very specifically about HV cables, whereas this does apply for nearly every single electrical asset you can do, including even protection. The protection model is very interesting. So this is the rough flow of what we did for this client. And rather than go through all the nitty-gritty specifics of how we do the math and everything like that, we thought the best way to show you what these models do is to run through what a client got with their data, how we collected the data, what the analysis we did, and what the client used it for in the future. So the first step is data. Like most analysis, it all requires good quality data in. And that's where this client was actually a bit of a step behind. They sat there and they said, well, we want to do this analysis, but we have no condition data. They didn't have anything really ready to go. So we did that gap analysis. We say, well, in an ideal world, these are the tests that we would recommend. And they did it. They couldn't do every cable on their network at once. So rather than sit there and just say, oh, we can't do it, they've got a plan in place where they do a selection of cables on a regular basis. Then we add that data to the model, we update it, and we give them the feedback they're looking for. Once you have the data, you start to look at all of the condition factors, all of the performance factors, how it affects the network, and what are the consequences of that cable having an outage. We combine all that and we get risk, and then we use that to look at what happens if you do different types of interventions and how will that affect your network and the risk of your network as a whole. So this is the rough process, and this is just what we did for this particular client. It does vary a little bit depending on different networks, but this is a pretty good overview. The first step is determine what are the health of your cables. And then we can use that to determine how much life can we expect to have left in your HV cables. From there, you look at what's the probability of that cable failing based on what its health is, and then what is the consequence of that cable failing. Combine it all to get your risk models, and then you can use those models to have a bit of fun and start to forecast into the future or into all different scenarios of different maintenance and different degradation. And you can have a lot of fun with that. So the first step being figure out the asset health. And as an asset engineer, a lot of us will be quite familiar with the asset health curve. So in the CBRM models and the CNAIM methodology, we basically grade where your asset is sitting on this health index curve. The one thing that we do not account for is infant mortality, because that's not really a condition-based degradation. It's more of an installation type problem. But if you're doing good condition monitoring tests, that should be picked up in those. So where we start is we figure out where it is on this curve, where we represent a 0.5 health index as brand new, and a 10 health index is severe degradation of the asset, full in end of life, needs urgent replacement. To do that, we combine a number of different things. So this client, we used age as the basis. Then we went and got all their condition monitoring results, their cable loading, their voltage utilization, all of the installation methods and locations of the cables, and we combined all of that into the asset health. So a lot of this data the company has, the age, the loading, the voltage utilization, the locations, and the installation method, that was all something they had in records, albeit it did need a little bit of cleaning to make it work in models, but the main component they were missing was the condition monitoring results. And that's where Brad and the service team came in. So we worked together, we designed the test that we thought we would recommend and would work the best with the models, as well as give them the best quality of results. Then we went out and we do that testing in set chunks every couple of years.
Okay, so the condition monitoring tests. So for this project, the following tests were chosen. So we did offline PD, we did offline tan delta, we did offline Lyra testing. Then we also did online tests, online PD tests, that is, while all the cables were in normal service. So for that one, we did TEV testing, ultrasonic testing, UHF testing, and we ran those tests while we were doing a visual inspection of the cables. So I said earlier, we could basically see most of the cables. So on this site, we were able to see around about 80% of the cables. So visually look straight at the cable, go up and touch the outside of the cable. The rest of it was buried either in tunnels or direct buried into the underground in conduits and things like that. So when we did our visual inspection, we looked at the installation condition, the visual condition, and the joint condition. So when we did our offline test, we went up to 1.3 times U0. That's our voltage level, so 30% above your phase volts. This one, we run through, locate, measure, and figure out where the PD is on the cables, if there is any. And then it all gets classified into those 5 classifications you can see down there below that fit into the CBRM model. So no PD confirmed, low, medium, high, not confirmed, or high confirmed. Then we did offline tan delta testing. So for each of these, we ran that at 4 different voltage levels. That's 0.3, 0.6, 1, and 1.3 times your phase to crown volts. We used the standards from IEEE 400.3 to classify them, whether it was paper or plastic. And at the end there, for the CBRM, we classified them into those 4 for condition brackets, which is no action required, further study advised, action required, or repair before replacement. Then we did our offline LIRA testing. So this one here is it's basically like a time domain reflectometry test with a frequency sweep all involved in the one test. That's a very generalized way of describing the LIRA test, but it's able to find localized degradations, differences between the phases and all that sort of thing. And those ones were classified into red, amber, green, depending on the test results. And these are all offline tests. So we turn the cable off. The first two tests, you inject voltages. This one here, you don't inject any volts. The LIRA just injects, say, like a 10-volt signal. So that's the ones that we ran. Then we have the online PD testing. So we did this while we walked the line. So we were able to go into all the substations, test where the cables go into the back of the switchboards, see where they came out underneath the switchboards, see where they go into the tunnels, see where they come on up onto the trays, see where they terminate into their respective cable boxes out in the field. And all the way along, we ran TEV testing, ultrasonic testing, and UHF testing. So if no one knows what that looks like in the field, you can see the three there. The one in the bottom left is UHF testing, where we get a directional antenna and point that at the cables and the joints and the terminations. The one in the middle there is Thomas, Exhibit A, doing an ultrasonic test into a cable box of a ring main unit. And the one on the bottom right-hand side there, I think is either me or Neil. I can't actually tell, but we're TEV testing the cables just underneath the switchboards. Again, they were ranked into red, amber, green. And then when we did our visual inspection, so they were put into the 4 condition brackets of no deterioration, limited, moderate or substantial. On this particular site, we found a lot of failed cable ties and clamps. So the cables were falling off the trays because they weren't secured properly. Damaged cable trays themselves. So some of the trays had been damaged due to they'd just been there a long time and the brackets that were holding them onto their structures had fallen apart. They'd failed. Sometimes it looked like a vehicle had ran into the tray and that had been smashed off and those types of things. We found a lot of corroded cable screens and glands and lugs, and we also found a lot of punctured outer sheaths. So sometimes the outer sheaths were punctured and there was salt water getting in and rusting out the screens and all that type of thing. So it was well worth walking along and finding those local degradations. And then overall the cables, once we had all the test results, this is over this is since 2016, we've put them all into these 5 sets of condition monitor results that go into the CBRM model. So you can see on the top left there, offline PD results, most of them had no PD. A couple that had low and a very small amount had medium in terms of its ranking. Or not its ranking, but its level. TAN Delta results, most of them were no action required. Some were further study advised, some were action required. The LIRA results, every single one of them was green. We didn't find any defects, localized defects with the LIRA tests. And then our online PD tests, most of them were green, 1 or 2 were amber. And the visual inspection had the most tapered results, where some were none, some were limited, some were moderate, and some were severe.
And on that, one of the things that's really quite interesting about this particular case study, and the reason we're talking about it, is it has 2 things that are significantly different to most other CBRM models and cable networks. The first is that you could visually inspect the large majority of cables. That is a luxury that most HV networks don't have. Most HV networks don't have the ability to walk the line and to visually see every joint in the condition of the cable. So that was a really good luxury and we could do that. The other one is that because it was a smaller subset of cables, we could actually change how we did the analysis. When you're doing modeling on cables, you have a couple of different ways of going about it. When you're looking at thousands of cables, traditionally you might model a cable run as a whole, independent of the number of joints or anything that's included in that cable run. For this particular site, we went about it a bit differently and we modeled each individual cable segment. What that allowed us to do is use the data for each individual cable segment, because a section that has an old section of paper lead cables, followed by a small section of XLP for a failure where they had to put in a new section, then mapped paper lead. All of those different sections have different expected life, different ratings, different manufacturer recommendations. So by modeling them in individual cable segments, which we could do because we were dealing with a lower number of cables, we were able to really give a very granular outlook. It's not always necessary, and a lot of the time when power companies do this model, you do it as a cable run, but you then have to take the worst possible of each cable run. If you've got one section that's failing, if that goes, it'll still take down the entire run. So it's just something that's quite interesting that we're able to do here that we wouldn't traditionally build into the models. Oh, sorry. So from there, we gathered all of the condition data, and it was really good of the company to make that leap and decide to start capturing the condition data, because this testing started back in 2016. And if the engineers had sat in that office and they gone, well, we don't have any condition data, there's no point doing it. And that's where they stopped. It would be nearly 10 years on and they would still have no condition data. They needed to make that leap and they needed to put the effort in to significantly bring up their levels of data so they can start to make informed decisions, because otherwise they wouldn't be able to see these models and they wouldn't be able to make the decisions that we're going to talk through now. So other than condition data, the things that go into the health index are the asset age. So you hear a lot of people start and they say age isn't the best indicator of health. And this is a pretty good example of that. Whilst it's not the best indicator, it is the basis of these equations. And I was talking about the thought process of an asset engineer when we come to you and say you've got a problem. Normally, the first thing you think about is how old it is. So this particular network is an aging network. We've got 55% of their cables would be considered midlife or higher, and that's quite a lot. For these models, we do use expected lives, and we do get these from the cable types and the manufacturer recommendations. These can shift for different networks based on what you're experiencing, but for this particular company, we use XLPE cables having an expected life of 40 years and PILT cables for 60 years, which is a pretty widely accepted standard. What's interesting is when you start to look in the future. So in 10 years, their network is going to significantly age, with 97%, all but one, cable being over 21 years old. You've also then got 30% of the cables will be 35 or more years old. And that's a significant number of cables when we're looking at age only that are going to be approaching the end of life. So the other analysis process that we use is cable loading. So for this, we've got the past 12 months of cable loading for each of the cables, broken down into 5-minute chunks, I believe. And we looked at both the average and the peak loading, and then compared that against what each cable segment had its manufacturer's recommended limits. So on average, we found that every single cable was significantly lower than what the manufacturer recommended. And by significant, I mean fractions of what it was. But the odd thing is the peak loading on nearly every cable exceeded what the manufacturer recommended, which is quite an odd scenario and not something you'd traditionally get in an electrical network and power companies, but it is something you'll see in industrial sites. And when we talk to the engineers, we kind of came to the conclusion that it's due to the inrush of when they're turning on their motors and different machines. But the time period of that peak loading was really quite short. And once we got rid of it, we actually determined that the outliers, the peak was significantly lower once we got rid of that inrush. So we looked in it, we did some modeling, we double checked, but in the end it was determined that that inrush period of the peak loading was too short for it to cause significant cable degradation. As a sense check, once the models were built and everything worked, I did run it, including the peak cable loading, degrading the cables, and it didn't make a big enough of a difference that we were particularly worried. If it did, and it significantly reduced the life of the cables, we probably would have looked into that a little bit further, but it wasn't a huge effect. So then we looked at things like voltage utilization. Quite simple, but we found that 23% of these cables were running at significantly lower voltage than they were rated for. So 9 of them were running, they were rated for 11 kV use and were running at 6.6 or something like that. And this, as quite a positive effect on your cables. They're not being run anywhere near as hard as they can be, and it does extend the life. From there, the other main components were the cable location and installation. So as Brad said, the majority of these cables are in trays, tunnels, with a couple being direct buried. So again, because we're looking at individual cable segments, you can actually have in a single cable run a combination of all the different things. So being in direct buried is what's considered normal in these models. It's what the majority of cables worldwide are. So being out and exposed, and as Brad saw, there was significant damage to those cable trays that were exposed. So that actually can reduce the life of the cable overall in the models. The location also comes into effect. Because geographically this site was quite close to the water, and as Brad said, there was punctures in the sheaves and they were getting rusting of the screens. So that location physically affects the health of the cable. However, it only affects the cables which are exposed. So direct buried cables, the few they had, their health wasn't lowered based on the fact they were close to the ocean. And this is just what we did for this particular model. You may have a very different network, a very different geography, and it may change for you, and it can all be factored in. It's just a matter of making the models and calibrating them for your network. So once we combine all them, we get our health indexes for every cable segment. And that's when you can start to have a lot of fun. So in the top right graph there, you have the health indicators of the count of each cable segments in the health index. So we can see in the top graph, most of these cable segments right now in 2023, when this work was done, the cables are in quite good health, with maybe one in the 5 to 6 bracket, which is starting to approach being more degraded. But we know lots about HV cables, and the models know the degradation rates. So what we can actually do is take their current health and forecast that into the future and say, well, what will it look like if I just leave this as is? If these degrade naturally, what will it look like? And you can see in 10 years, there start to be a couple of outliers that are really moving into that severely degraded area of their life cycle. And that is if they do nothing, which isn't particularly helpful because our job as engineers and asset engineers is to do smart maintenance regimes. So what we then started to do was run different scenarios. And we said, well, let's look at 10 years in the future, but rather than doing nothing, let's say that they start to fix all the problems that Brad identified on site. If they can do repair to cable sheaths, if they can fix the cable trays, they can do all the little bits and pieces that was causing the health to be a little bit more degraded than it would naturally. So, and you can see the very significant difference. The top graph shows the cable health if they do nothing, and then the bottom graph shows the cable health if they do smart interventions. And there's a really big pullback of the cable degradation, and it in turn increases the life of the cables. So for us, we ran this on what we would call modeling scenarios. This particular example I'm showing here isn't the most realistic. It's if they managed to do every recommendation Brad made, they managed to do it perfectly, and they managed to do it in 2023. The reality is for bigger networks, you may not be that lucky. So I'm going to talk about a bit later on if you can actually start to do planned maintenance programs and factoring it in, which gives you some really interesting data. But once you have the health of the cable now, and you know how long you're expecting that cable to live, and you know the degradation of the cable, you can actually start to estimate the estimated years to end of life. And that is a really powerful tool. So what our graph here shows is every single cable segment that was tested. It shows what its total expected life was based on its current health, and then what that can be reduced to, or increased to, I should say, if you do the interventions that we recommended. So what's really interesting about this is it shows you the direct effect of certain maintenance programs. You can say, well, I'm going to spend a bit of money, a bit of time, I'm going to do all these recommendations, and I'm estimating to get another 10, 20, 30% out of that cable's life. And that's a really important thing. It also brings to light where you want to be focusing on, because if I'm an asset engineer, I'm looking at my cables and what I need to be acting on the next, 2, 5, 10 years, my eyes would be going directly to the cables from 23 to 27, with that ones that are very much approaching that end of life. And that's where you'd be looking to spend your money and your time focusing on. But that's not where it ends. And you can stop your modeling at the health index, but it's one of the things that admittedly both Brad and I do. If we tend to hyper focus on a single asset, and these tables are really good. It tells you what your asset health is and what it's doing. But the next critical step isn't just what's the health of that cable or what the health of that asset is. It's what role does that asset play in your network? And that's where you start to get your smarter investment decisions. Because if you've got a cable and it's at most industrial sites, you will see you've got a couple of, might feed a water pump that you don't use often. It may be quite degraded, but it doesn't play as pivotal of a role in your network as another cable which may be less degraded, but is very critical. Common sense dictates that you're going to put a little bit more focus onto your main incomer at an industrial site than you are on the right end of a feeder. So it's a really important toss-up. And to do that, we start to do risk analysis. So risk analysis is where we take your asset health, we then know where it is in its life cycle, and based on statistics and probabilities of failure, we can determine what the chance of your particular asset failing are. But then we need to know what the consequences of that asset failing are. And to do that, we looked at 4 main categories. You've got your network performance, what happens to the network if that cable fails or de-energizes. Then direct financial costs of what does it cost you to repair that cable. But then you've got your safety implications. What if there's a failure in that cable and someone does get hurt? What are the chances of that? And what would that actually cost your business? And then as well, you've got the environmental costs. And in Australia, environmental costs cannot be ignored. We've had a number of quite severe bushfires caused by other types of assets going through failures, and that's had rather large roll-on effects. So the environmental costs can be quite big, and it does change per asset. I've worked on things like oil rigs, where they treat oil-filled transformers very seriously, because if you dump that oil into the environment, there are very big environmental costs associated. So every site will be a little bit different, but they cannot be ignored. So once we have that, you start to think about not all failures are equal. So we actually break it into 3 main failure categories. There's incipient, which is your really low level, tiny things, small degradation. These are the incidents that you're getting to early and you're finding with your condition monitoring tests. So an incipient failure is what we'd say low-level PD sources, where you're finding things that may lead to failure in the future, but they're very, very low level. You've got degraded, where there's a bit more significant, takes a bit more work to need it, to fix it. So rather than just cleaning up a cable term, for instance, you may have to redo it. Then you've got your catastrophic, which we can all picture what a catastrophic failure is. And each of these categories has a different probability of occurring. It has different outage costs associated with it, different repair costs, different safety implications, and different environmental effects. And it changes the ball game significantly, and it changes per asset as well. There's differences to if a transformer fails, to if a direct buried HV cable fails. And that all needs to be factored in when you're looking at the probability of failure and its effect on your assets. So this is what you end up with. Once you go through and you look at what is the outage cost. So you say, well, this particular cable, if it goes down, it costs me $20,000 an hour. For energy companies, those numbers are really well documented. You have all your regulatory fines and everything like that. For industrial sites, it tends to be all network performance. You know what you're producing, you know what you're exporting, and you know what's going on. So for this particular site, network performance dominated the risk. The main risk for this site is if a cable de-energizes, they lose production. There's a small safety risk associated, then a small financial risk for the repairs. That on this site was actually probably bigger than most other industrial sites, because this particular site didn't have a high voltage electrical team on site. So if there was even a low level failure, they have to get someone in, which is normally had a higher turnaround than an energy company per se, who has people on site responding directly. From there, excuse me, from there, we start to do the same modeling with interventions. So this is looking at our 10-year projection of if we do no interventions. But then we look at the 10-year projection if, again, we do all those interventions that Brad recommended. And you can see that network performance-wise, the risk. So by reducing that probability of failure, because the consequences don't change, it's only the probability that does. So you go from having nearly $900,000 of network risk in year 10 to under or around the $500,000 mark. And that's a very significant drop in risk on these assets over 10 years for doing what was quite easy to do recommendations, fix cable trays, fix outer sheaths and different things like that. There weren't too many very drastic recommendations that we did for this particular client. But in total, you can see a very significant reduce in risk. And this is what asset engineers use as your justification. Because you can sit there and you go, well, this work that I want to do, and you run the scenarios. I want to do it on this cable. That cable is currently giving me $100,000 of risk in year 1. If I do the maintenance, the risk might drop down to 20,000. And I expect the project to cost me 40. So you're in a net win in that scenario. And it's really good justification. And justification like this is used by energy companies and the regulatory submissions. A bit more in depth, but it is the general idea. So then you start to combine it all. And this is replicating the table we saw a bit earlier of looking at each cable segment. But now, rather than looking at the asset health, we're looking at the financial risk of each cable segment if we do the interventions versus if we don't do the interventions. And this actually paints a very different picture. So we can see that earlier on, we saw down in the segments of 1, 2, 3, 4, we did have a significant increase in asset health if we did the interventions. But those cables weren't as critical to the network. So doing and spending that money to do the interventions doesn't actually reduce the company's risk as much as if they focus their time and efforts on this middle section where you can see the risk drops significantly by following it. And it helps you really see where you can target your spending and where you can make really good use of your money in order to make your network more stable and work better for the entire company. And this is where we stopped for this particular client. We went through, we ran all different scenarios, and they used that in their long-term planning. But you don't actually have to stop here. You can be quite intelligent about it if you want to. So where the most intelligent, where the most fun, in my opinion, comes into it is with your more advanced intervention models. So as I said in this, we did in the top section, we modeled scenarios. We went through and we changed data and we looked at what its outcome would be on the long-term forecast. But you can be a little bit smarter than that. If you've got a really big network, you can say, well, let's say I can commit to every year I will do maintenance on the top 5% of my the highest health indexes or the highest risk. And then you can see in every year it will bring them down because you're not going to do everything in year 1 and it will stagger them across the forecast you're looking at. Or you can do really targeted, say I want to hit this, this and this in these particular times. You can also put in the difference between what if we're replacing as new, what if we're doing maintenance, and what if we're doing a refurbishment? Because if you go and do maintenance on an asset, it doesn't actually bring it back to as new. It helps the health index, it gets rid of some degradation, but we wouldn't say it goes back to the exact same as a brand new asset. So it's all different things you can factor in. Then if you want to get really quite intelligent, you can do the full asset management program where it puts it in, you put in a schedule, it pumps it out, and then it brings health indexes down at the right points and times. It tracks them. You can do full portfolio optimization if you wanted to. You can then track them over their life cycle. You can see the trending of their health index, and it works really well. And that's your more advanced. It uses a little bit more data, but you can have fun with it. The next thing that I find particularly interesting is what you can do with risk reduction. And risk reduction can be done in a number of ways, but the one that I'm particularly good at and do a lot is permanent monitoring. And the effect of permanent monitoring on your assets and on these models is actually a little bit counterintuitive in a way, because a lot of people think it would be acting just as a condition monitoring test. The same as going to site, only a bit more accurate. Maybe it can be weighted a little bit higher, but it doesn't actually always work in that way, because what condition monitoring does is it doesn't actually prevent any failures. It gives you a chance to get to that failure before it snowballs and becomes catastrophic. So rather than being factored into the health index and the degradation of the cable directly, we can factor it into the failure rates and the breakdown of failures. So on the right there, you can see two failure breakdowns. And these are actually for circuit breakers, not HV cables, admittedly. But most of the failures we were seeing were catastrophic because they were getting there, they didn't have monitoring, and they were going to that level of failure quickly. However, with the monitoring, that level of catastrophic failures is significantly decreased. The failure is still there because the degradation still happens, but the company is able to identify it, they're able to get to it quicker, do the maintenance, and that's where the saving comes in. Because Brad and me have seen multiple times, if you can capture a problem in its earlier days of degradation, the outage, the repair time, and everything like that is significantly lower. If you can divert one failure from being an unplanned catastrophic failure to a planned maintenance on a degraded failure, even if you still have to do the day's worth of work, it's significantly cheaper than that catastrophic failure. And that's how you can apply permanent monitoring to these models. It's not necessarily just a condition test, it's also diverting the failure types, and it's really interesting to see its effect. The other thing you can also start to do is decrease the degradation rate of a monitored asset. So if you've got an asset that you know you can get to quickly the second a problem appears, you can get to it, then that particular asset would be degrading potentially less than a non-monitored asset because you're getting there and you're doing the repairs quickly. And that in alignment with the fact you're having less catastrophic failures has a massive effect. So this here is a model from what would be an incomer of a main industrial site, where they're looking at about $450,000 of loss on a day if that incomer fails, which is pretty reasonable for a lot of sites. And what we've got is the 10-year risk forecast of that cable based on all of its condition tests. So this particular one, I modeled that it did have a PD issue that was known, and it had relatively good condition tests otherwise. And you can see that over 10 years, you go from a little bit more than $500,000 risk up to a little bit over $2 million per year risk if you just let this go with no interventions. However, if you put a monitor on it, you can reduce that risk down by changing the probabilities of that catastrophic failure, and you significantly lower the amount of risk per year. And then the bottom is, you can just see it poking the head out, is what the risk would be if you justified a full as new replacement, which for a lot of industrial sites just is not viable. But it's always an interesting comparison between what will it be if we do nothing, what will it be if we do monitoring, what will it be if it is as new. And that's something that can really benefit you when you're looking at the different justifications of projects. Because if you're looking at doing a big monitoring program and it costs $50,000 a year, and you can reduce your risk in year 10 by nearly $150,000, $1.5 million, it's a very justifiable project. And the same can be done with any project that you're looking at doing. If you can justify that it will reduce the risk monetarily and that costs less than the project itself, then it's something that is quite justifiable in the long run. But it's really interesting to see the effects. And that's the bulk of our presentation for today. But in summary, we didn't go through too much of the technicals, but it's all about what we did with this client and how we use this analysis to help them trend into the future. And it allows them to develop their interventions models. And without these types of models, a lot of engineers have a pretty good gut feeling about what their network is doing. But it's about getting numbers you can stand behind, numbers that you can trend easily, and numbers that you can work with on a holistic network-wide scale. Asset health and the health indexes are a really crucial part of that. Knowing the current condition and the degradation rates of your assets will be really helpful in your planning. But taking it that step further and starting to look at your network as a whole can really give you some insights that you would otherwise miss, because it takes into the little bits and pieces and your network and factors it into the asset as well. And doing all this can work really well for your interventions models, and it can show you the direct implications of it. And that's us. I hope you really enjoyed the presentation. We can do meetings to talk about what data you have and what data the models can use. So if that's something you're interested in, please feel free to reach out to either Brad or I. We're on LinkedIn, you can email us, and we can really talk through what the process is, how it would work for your company, and what you can get from it. Because at the end of the day, it's all about how this can work for you. Cool. Other than that, we haven't had any immediate questions come through. So thank you very much for your time, and we hope to see you at the next webinar. Thank you.
See you guys.